We all know that technology has transformed the healthcare sector, improving people's well-being and quality of life. But still, there's a lot of room for innovation and improvements. There is a medical device that's used daily in every hospital and is crucial for patient care, yet that device is full of limitations. The one we're talking about is the patient monitor. Vital sign monitoring is a common practice in patient care that aims to detect and diagnose medical problems through tracking changes in patients' health conditions, like irregularities in heart rhythm and breathing activities. We followed the design thinking approach, where we first needed to understand the patient's problems. Although the traditional vital sign monitoring methods used in clinical settings are generally accurate, these methods require direct physical contact with the subject's skin through electrodes and cables. This direct contact imposes several limitations, and it's even not suitable for some patients. For instance, patients who suffer from skin burns, with 30,000 people daily suffer from new burns worldwide. Many of such are severe burns that make it difficult to use conventional stick-on electrodes, and invasive or painful methods would usually be used instead. Patients with sensitive skin, where 2% of the population, which is more than 160 million people, would suffer reactions due to the electrode's adhesives. It could cause rashes and might even cause burns, especially in the case of infants, whose skin is very delicate, which makes attaching the electrodes difficult. Also, physical contact increases the risk of hospital-acquired infections. Finally, this setup is typically bulky, constrains the subject to the location of the monitor, is generally costly, and requires professional training. So now that we've defined the problem, we then move to the next phase of design thinking, which is ideating and finding a solution to the problem. The drawbacks mentioned motivated the search for a vital sign monitoring method that doesn't involve direct contact with the patient's skin. Our motive is to develop a real-time system that measures vital signs in a non-contact manner, both accurately and continuously.
We have carried out market research and studied existing solutions. The researchers investigated a lot of different methods and sensors, including RGB and thermal cameras, visible light sensing, vibration sensor under the bed, and radar sensor. As for existing products, Apple Watch gives the user the heart rate and respiration rate, but for the ECG, the user is required to stay still for 30 seconds with touching a specific button. Therefore, the ECG is not continuously monitored and it still requires some physical contact. After doing extensive research of the various technologies that have been investigated for this purpose, we decided to use radar technology, where we use millimeter wave frequency modulated continuous wave radar, a sensing technology that has been used in multiple published research and has proven accuracy for measuring some vital signs. Also, radar doesn't invade privacy like in cameras, has greater penetration than light sensing and infrared cameras, and it is not affected much by environmental conditions like illumination and temperature. To ensure that our idea is accepted by the medical staff and the people, we have made a survey to ask medical and non-medical people about their experience with the traditional setup and how open they are for the alternative we aim to develop, where over 300 people from different ages and genders took the survey. 50% of the respondents worked in the medical field. We asked the non-medical respondents whether taking off their clothes and attaching electrodes bothers them, and the vast majority confirmed their discomfort. As for the medical personnel, we have asked whether the traditional method wastes time and needs professional training, and if they would trust the results of a non-contact alternative. The responses came positive and we are open to a non-contact device for monitoring. In order to utilize radar, we had to study and understand radar basics and all the needed physics for this purpose. Our system targets the heart rate, respiration rate, and electrocardiogram. It has software and hardware modules. The software includes the heart and respiration rates module, ECG module, and the application layer that controls the hardware and harmonizes the flow of data to the processing modules and out for display. The hardware module on which the software one is deployed consists of a Raspberry Pi microprocessor and an LCD for displaying the vital signs. Due to the scarcity of the data, we developed a GUI-based simulator for generating synthetic radar and vital sign data that is used for the validation demo where the data is sent to the hardware module. We also collected our own dataset using the Texas Instruments Frequency Modulated Continuous Wave IWR6843 Research Board with the DCA1000 evaluation module, which works as a bridge for data transmission to the PC. We managed our project through weekly checkpoints to check our progress and distribute the tasks according to each one's expertise, where some members worked on the digital signal processing and hardware parts of the project, and others worked on the deep learning and data collection part.
Now, let's talk about our implementation phase, starting with the software module. For the heart rate and respiration rate module, we tested various algorithms and selected the method suitable for real-time processing constraints. We used the synthetic data from the simulator with specific signal-to-noise ratio levels and configurations. In the following diagram, you can see our online processing pipeline. Since it depends on data seen till the present moment to extract the heart rate and respiration rate, the mean absolute error starts with a high value, then decreases exponentially as time passes. The level of noise added to the data affects the time of conversions and the oscillation of the curves. As for the ECG module, we have contacted the authors of a paper and gained access to their dataset. We implemented an architecture that follows a similar approach of the authors using PyTorch, but modified a few blocks. We also tried an autoencoder architecture and an LSTM of several layers, since it is suitable for the time series problems. In the end, we implemented an architecture that consists of an encoder part that involves a convolutional layer followed by a decoder of LSTM layers. This architecture gave better results than the two former ones. With our limited resources, we trained each of these models for 200 and 300 epochs, and this table shows the summary of the results. Here is a sample of the predicted ECG of the encoder-decoder model to the left and the encoder-LSTM model to the right. This is the simulator we developed to generate synthetic data for the testing and validation phase. The user can control the radar configurations and different scenarios of the surrounding environment through adding humans with the heart rate and breath rate and the static objects. After the data is generated, the user process starts streaming to send the data to the Raspberry Pi where our algorithms for vital signs extraction are deployed. Our current system provides the heart rate, respiration rate, and heart rate variability. Most importantly, our system is immune to patient movement due to the human localization step in the pipeline. The deployment of the ECG module on the microprocessor is still in progress.
This is our demo for testing and validating the system. Using Visual Studio Code, we run the simulator on the laptop, choose the preferred radar configurations, play the static objects, and choose the heart rate and respiration rate for humans. We then generate the signal and begin sending it to Raspberry Pi by clicking the button Stream. On the LCD, you can see that after some time enough to detect the vital signs, the values and waveforms are displayed and updated periodically. In the end, we gathered our own dataset that can be used to further improve the system and assist in future research in the field. The data collection was performed at a hospital. We collected the radar signal alongside the synchronized ground truth, heart rate, respiration rate, and ECG signal. We have used the IWR6843 port alongside mmWave Studio software, a GUI offered by Texas Instruments that provides the ability to configure and control mmWave sensor modules from the PC and collect digital data for offline analysis. As for the ground truth data collection, we have used GE Healthcare CareScape P650 and P850 monitors, where we developed a serial-to-serial connection between the monitor and our PC. We have used iCollect, a software provided by GE Healthcare to control the collection and store the data received from the monitor. We purchased a holder to be used in data collection and as a body for our prototype. We 3D print an extension for it to use the attachment for the components. We can control the angle and the distance between the sensor and the subject through a holder handle. This is our final setup for collection. We collected a total of 3.5 hours of radar and ground truth data from 24 healthy volunteers and 3 ICU subjects, 16 of which were females and 11 were males. The subjects' ages ranged between 17 and 64 years old, with a modern median of 23 years old. We would like to note that during the collection, the subject showed discomfort due to attachment to the electrodes, and the readings of the monitor were affected by the presence of the hair and subject movement. This made us even more certain that our system will facilitate vital signs monitoring. This Gantt chart shows our progress. For future work, we can enhance the results on the heart rate, respiration rate, and ECG modules and finish the embedded system implementation by incorporating the ECG module and connecting the Raspberry Pi to the IWR6843 industrial chip that TI Instruments have provided for mass production instead of the research board. We believe that our system with no skin contact, no risk of entanglement or patient discomfort, no infection, as well as no need for professional training, will streamline several operations in vital signs monitoring field. Having such a device will surely support medical personnel who need to make rapid decisions in emergency situations and also facilitate monitoring for subjects in home care and in vehicles.